Good. I can also turn my camera on, of course, that you see me again. So sorry if this all is a bit chaotic. This time not the technology failed, but well, the technology failed because she cannot log in with her computer. Good. So it looks like the YouTube is live. Then I return the hosting rights to Xiao Hang. Good. So Xiao Hang, you're the host again, but I will start the session by sharing my slides. Good. So I hope you can all see it now, the slides. If not, please protest. Actually, I can look at it myself in the other video and on my other computer. Because we have a live video stream now on YouTube. Good. All right. Xiao Han, could you also please start the recording now? Is the recording started?
Yes, it's
Oh,
now
okay, good.
recording.
Sorry, I don't see it here because I have shared my screen. Okay, welcome everyone. For those of you who haven't been here yesterday, I'm Wolfgang Hurst, one of the general co-chairs. The reason why I'm in here again today is that yesterday in my introduction I already said I'm going to split it in two parts. So oh, I see now 7 is in. So Xiao Hang, you can also promote her if you find her in the list of attendance. Good, yeah, the 7 is the session chair. She had computer problems, but I was planning to start this session anyhow before handing over to her because I already said yesterday that I will split my introduction into two parts. So welcome to the second day. And we have the keynote now. And before I start with the before we start with the keynote, I want to quickly talk a little bit about the conference program, about the papers that we have. So here we have the statistics from the acceptance rate. Full and short papers together are 27.3%, so relatively low or quite low actually for a new and small conference like us. Kind of also consistent with the first 2 years. Now, the reason why we're this is usually the combined for full and short paper that we're reporting. And the reason why we're combining full and short papers is because they are both from the first deadline that we have, where we also have the same program committee and the same detailed review process. So also the short papers have been reviewed in the same way as the full papers by at least, I think, 4 reviewers had each paper, plus a meta review from the program chairs. Then we have a second deadline where we have then posters, special sessions, industry papers, and demos, where and the reason why we have this second deadline is, of course, that if we have posters, they contain, of course, also late-breaking results, work in progress. But for the full papers and the short papers, we need also longer time to do a thorough review, which is why we have this split review process. And you see also, of course, the posters, because they contain also work in progress, they have, of course, a higher acceptance rate, but still the acceptance rate isn't too high. So you see here also the posters and industry papers and special session papers have been very thoroughly reviewed. The reason why we have 100% demo acceptance rate is that this year we only got 3 demos submitted. So these are the submission rates, but with the absolute submission numbers, we are also doing quite well. We're the third time now, the third time that we have the conference, and each year it's increasing a little bit. So we have 25% more submissions on the full papers this year, which is quite nice. Overall, the numbers are not huge, but still we're growing. So I think we're doing quite well. We have an increase everywhere except for posters, industry, and demos this year. I think this is, of course, probably also COVID related. Not only that people were not able to do the work, but the deadline collided a little bit with where the academic year started in most countries. And because of COVID, people were even more busy than they are usually with when they start a new academic year. So that is, of course, a little bit unfortunate. But yeah, overall, I think we're doing quite well. But of course, as a conference, a scientific conference, we're not just interested in the quantity, but mostly in quality and also the content. So it's also interesting to look into what type of papers we got, especially since we are a relatively new conference, only the third year. And this is a little an overview of the different communities where we thought AI and VR should be relevant, because of course when we started AIVR, we also there were a couple of people who said, "Oh yeah, this is great. These are really interesting and cool topics. It's important to bring them together." But there were also a couple of people who said then, "Yeah, do we really need another conference?" And it's like Phil said, like I mentioned yesterday, like Phil always says, conferences are not just about the papers, they're about the communities and bringing people together and creating communities. And these are, of course, the communities that we were hoping. And if we look at the program, it's actually really nice. It's a really nice mixer. So we basically have from each of these communities, we have submissions, including even the ethics community. So we have the ethics workshop running in parallel today, not parallel to this session, but parallel to the first and the last session. So if you haven't checked out the first session, they're still having a second session afterwards. And I think they're also closing with the keynote. So if you're done with the process, you're very welcome also to join their workshop. You can also join it at the beginning, of course. So we're actually doing quite well here. Yeah, so we get input submissions from all these communities, but another concern that we had at the beginning was, of course, also that we end up getting kind of like the papers that are rejected at all these events, because yeah, we are a new conference, and of course, it would be arrogant to say we can compete with SIGGRAPH or with IEEE VR, and this is why we think it is so important to build a community, because we cannot compete with SIGGRAPH and IEEE VR and all those top conferences when we just put out the call, but we can compete with them when we say we have a community, we're creating a community where people say, here, if I go to this conference, I meet the people who are really interesting for my work, who are really interested in my work, who are really relevant for my work. And I think we're doing actually quite well with that. So I see a lot of returning people already after the first 3 years, but I also see always a lot of new people coming in. So I think we're actually doing quite well, and I'm quite happy with how it's developing. So I think we're doing quite well here. One thing that I'm 100% sure we are doing very, very well already is in attracting very good keynote speakers. And this is the part now where I want to hand over to the actual session chair, Serin. Now let me stop the sharing here. And let's see. Is she in the audience now? Is she? I see Philip is in the audience. So Xiao Han, could you please promote Philipp Slusallek to panelist? Did that work out?
Yes, but I have
don't
said,
see him
but
in the attend.
yeah,
I don't see him in the attendees anymore. But I don't see him as panelist either. Did you kick him out? Hopefully not.
No.
No, here he is.
Okay.
I was afraid, Philip, we kicked you out. We wanted to promote you, and
actually,
suddenly
that is exactly what happened. I got kicked out but yeah, I'm back.
Oh, sorry, but now you're back. That's great. And I also was missing. Could you also promote Seren Yumak as panelist? She's at the very bottom. Yeah, here she is, panelist. Seren, does it work? Quick update for Philip. She had computer problems, so I think she's joining with her phone now. Is that correct?
Yes. Can you hear me?
Can hear you and can see you. For me, it works perfectly.
Yes, great.
So then I hand over to you as session chair.
Yes.
You introduce Philip. I haven't done anything. So, if it doesn't work out, let me know, then I step in.
Yes, great.
Perfect.
Okay, good afternoon, everyone. So first of all, apologies for this technical problem. Actually, at the last moment, I have some problems with my PC, so I have to connect over the mobile phone. But nevertheless, I am here. So yeah, I'm very happy to announce our second keynote speaker today, Professor Philipp Slusallek. Professor Slusallek is scientific director and member of the executive board at the German Research Center for Artificial Intelligence, DFKI. And he heads the research area on agents and simulated reality. At Saarland University, he has been a professor of computer graphics since 1999, a principal investigator at the German Excellence Cluster on Multimodal Computing and Interaction since 2007, and was director for research at the Intel Visual Computing Institute from 2009 to 2017. Before coming to Saarland University, he was a visiting assistant professor at Stanford University, and he is the associate editor of Computer Graphics Forum, a fellow of Eurographics, and a member of Acatech, which is German National Academy of Science and Engineering. His research covers a wide range of topics, including artificial intelligence, simulated digital reality, real-time realistic graphics, high-performance computing, motion synthesis, novel programming models, and many others. And today he's going to speak about digital reality from AI to synthetic data and back. So we are looking forward to your talk. Thank you for joining us today.
Great, thank you very much for the introduction and of course also for the opportunity to give a keynote talk here at this renowned conference. Glad to see you all, well, not see you, but be able to address all of you here in the audience. Looking at the program of IEEE, it's clear that AI and AIVR, there's a lot of commonality here. And so I think it's great that I can talk a little bit about the work that we're doing and how AI, at least from our perspective, how AI and AR/VR, how they could work together. And I think hopefully I can share some of my insight into that, and I'm happy to engage with you in the discussion afterwards. So maybe very quickly, a little bit of background on myself. I'm actually originally studied physics, then moved into graphics, got my PhD at Erlangen University with Hans-Peter Seidel, then moved to Stanford as a visiting assistant professor. And since 21 years, I'm now a professor for computer graphics at Saarland University. So still, that's my main profession, is on the graphics side. But since 13 years, I'm now a scientific director at the German Research Center for Artificial Intelligence. And so we're really trying to combine AI and graphics and high-performance computing, and I'll get back to that. So first of all, greetings from nice Saarland, part of Germany, right on the French border, including such nice views as this one. So if you are in the area, let us know, drop me a line and drop by. A little bit of background, what else is here on campus? We call it the Saarland Informatics Campus. So it's a state of Saarland, a German state. And here we have the university. Saarland University, mid-sized German university, full university. We have the two Max Planck Institutes focusing on computer science, obviously more on the fundamental research side, and DFKI, again, the German Research Center for Artificial Intelligence, more focused on applied research, but we also dig into basic research as necessary for our work, and I'll come back to that. The one thing that's really strong about Saarbrücken is the very close collaboration, and that's been apparent by the cluster of excellence that we got here some years ago, and also the new Helmholtz Center for IT Security, CISPA, which is on campus, and many activities that we're driving forward here. So a great place to do research. DFKI, one of those elements of the Saarbrücken Center is the largest largest AI, independent AI research center worldwide, founded in 1988 already, so 32 years old. We have 6 sites across Germany. Saarbrücken is the largest one of them. You see a map on the next slide. We actually have 21 research areas as of this month. So I need to fix this. Covering essentially all areas of AI, pretty much. We have 8 competence centers that kind of gather the competencies from the different research areas in key areas like deep learning and autonomous driving and others. About 1,100 staff, most of them in research and support staff, of course. We're growing really quickly, or probably in the order of 67 million this year, and many spin-offs. So just a little bit of background here. This is the interesting part about DFKI is we're actually a public-private partnership. We're a non-profit private organization, GmbH under German law. And we collaborate with many industry partners. You see some of the international companies like Google, Microsoft, SAP, NVIDIA, Intel, many companies from the, let's say, automotive industry, Volkswagen, Daimler, BMW, and many others, suppliers, but also retail, finance, agriculture, and various others. So it's a very interesting setup. And they are part of this because they want to engage with the research that we're doing. And this is what I mentioned before. We're not doing the blue sky research on the one end. We leave that to Max Planck Institutes and other basic research organization. Our main focus is here in the middle is the applied research and development. But as I mentioned, we go into the application-inspired basic research, where maybe basic research is missing to actually do our applied research that we want to do. And then we transfer that to industry, but we're not focusing on the exploitation and commercialization. So just so you have an idea of where we're operating here. DFKI is very international. About a third of our staff, but again, on the research side, of course, is international. And so we're also, I should mention, we're hiring both on the PhD level, so you can do a PhD at DFKI, but also at the postdoc level. So that's, and particularly this combination of graphics and AI is, I guess, not as usual, as common at least in the AI area. I want to mention one part. So DFKI is not just doing the AI research of focusing papers and projects, but we're also doing a lot of work and kind of bringing the community together. And in particular, on the European side, AI was highly fragmented. And so 2 years ago, 2.5 years by now, we actually founded CLAIR, the Confederation of Labs for AI Research in Europe. We're focusing on excellence across all of AI, specifically, of course, focused on Europe with a human-centered focus. You find more information on our website. But actually, as far as I know, we are by far the largest AI research association worldwide. Almost 400 labs from all over Europe joined forces here. Over 3,600 AI experts are supporting this. Countries are supporting this. Various big organizations, including the AAAI. So, and ESA, for example. So I think that's interesting, in particular, if people from the graphics and AIVR side, that might actually be an interesting way to meet and engage with AI. Just so that's why I wanted to briefly mention that. So one thing I want to say is give very briefly a little bit of perspective on what I believe AI is, and the structure of AI and the way we look at this, because there is sometimes, I think, somewhat weird perception of AI, and so I want to use the opportunity to kind of communicate the way how I look at that, and that to a large degree also determines how we do research in this field. So I think this is important. So first of all, the intelligence itself is hard to define. A lot of people define it as the ability or inclination to perceive and deduce information about the real world, and then to retain this as knowledge so that we can then later apply it in possibly completely different settings and in completely different environments, completely different contexts, and solve problems that way. And then AI is, well, some people just say, oh, it's the same thing, just done by machines. Others say, well, AI is really about cognitive functions that we know in humans and that we associate with humans, but the machines are mimicking them, they're simulating them. Are they really implementing them? There's some discussion, particularly also on the philosophical side about this. From my point of view, AI really is the study of intelligent autonomous agents or systems, if you want. And this can be easily seen, or this point of view, if, for instance, you look at how what is part of AI, and if you go to Wikipedia, for example, you see all of those points that are mentioned here. Unfortunately, and surprisingly for me, and not in this order, which makes a lot more sense, I think. It's essentially a version, a detailed version of that see, think, act paradigm that probably many of you have heard about earlier. So it starts with perception to kind of find out what the world around looks like. Of course, looks in various modalities, could be camera, radar, LiDAR, many other sensors, including digital sources. Crawling the internet is part of that. And then using machine learning, and that's where a lot of the deep learning is actually applied, to make sense of that perception data, of that sensor data, to essentially adapt or build models of what we're perceiving, of the reality around this. And the next step then is to use these models to represent that information, these models, to be able to process them in some form of representation, but also to communicate it between machines, but also to communicate between machines and humans. And that then partially also goes into that explainable AI direction. I'll come back to this a little bit later. The next step then is to reason about this, to integrate the knowledge that you are currently perceiving and representing in this knowledge base, and integrating this with other knowledge that you have, whether that's in a symbolic way or any other way, to generalize the information, to put it into context, infer new models out of that, the integration and so on. Then we're planning a possible action to reach whatever goals we might have. That often relates to actually simulating what we want to do, simulating our action, simulating how the world around us would react to whatever kind of action we want to do, explore different options and evaluating the relative performance. And then finally, based on this simulated, assumed evaluation of the performance of our actions, and make decisions of what our actions is. And actually, I think this is pretty similar to what we're doing as humans, right? Right. If you plan a trip somewhere, then of course you think about, should I take the train, should I take the airplane, or whatever, and what are the obstacles, and maybe the train isn't working, so you have to plan around that, and so on. But then eventually, once you have made a decision where we have to implement this, we have to maybe manipulate the world in any way, move around and in a possible AR/VR environment, and then of course start over And there's many supporting functionality that I don't have time to go into. And of course, this can be applied in many different areas. And in that context, sometimes people argue, what is really data science and data analytics in that sense, right? And from my perspective, but I know some people disagree, it's really just the first part of this pipeline, right? It's the perception, the machine learning part, the derivation of models, maybe also in many cases then the representation part, but usually very little of the reasoning, planning, and acting part, which I believe really is where a lot of the AI, core of AI really happens. So it's really part of the same thing. The other part I want to talk a little bit about is that AI really is a very, very broad field, an old field, very broad, and you can roughly subdivide AI into reasoning technique, which are probably more symbolic, and the learning part, which in many cases is more sub-symbolic. And in each of those areas, we have a huge collection of tools, of methods, right? Whether it starts from rule-based system to statistical reasoning and many variations of that in between. And on the other side, on the learning side, we have very traditional methods like reinforcement learning, support vector machines, and many others. But of course, in the last few years, deep learning has really been driven to the limelight and gets a lot of attention. But and that's fine. That's perfectly fine. It's a really important and powerful technique. But sometimes people kind of fold together AI and deep learning and machine learning into being the same thing. And I want to just really very clearly make the point that this is not the case. And actually, one of the areas where a lot of research is currently looking into, but including people who are deeply invested in deep learning, is really combining deep or machine learning with other techniques, whether that's reinforcement learning or including model-based approaches with learning-based approaches and deep learning networks and various iterations of them. And you can do this in various ways. So that's really, there's a very rich field and a lot of developments going on here. And then, of course, AI breaks down into various AI communities. Now, there are many more than are listed here, and we apply AI essentially everywhere now. So this is a little bit of where I think we're coming from. And sometimes behind all this really important work on deep learning, we sometimes miss some of the success stories of AI that have been around and that are hardly talked about, and some people don't even actually know, right? So for instance, hardware verification, right? Some of you might remember the FDIV bug by Intel, which cost Intel a fortune, right? $500 million dollar back then in old currency. So it's actually really was a lot of money back then. And that's 25 years ago, right? And you can imagine that how much more complex hardware got in the meantime with this exponential curve. But this kind of bug, we've seen other bugs, but this kind of bug and this is essentially hasn't happened. And essentially this is because of hardware verification. A lot of today's processors are largely verified. And so that's a huge success story, but it's not really associated with AI, even so verification, and specifically hardware verification, certainly is an area that grew out of AI and is largely perceived as a separate area now, and rightly so, but it's part of AI. The other thing is of course, knowledge graph. We can really have, and that's probably not celebrated enough, we can represent 100 billion facts and rules about the world now, and we can represent and process that. We can do reasoning about them. There are some scalability issues that people are still working on there. We can do very large parts of this, but reasoning about the entire set is still difficult. And that's really important because a lot of the deep learning stuff learns implicit representation and relating this implicit representation to explicit human understandable concepts really involves knowledge graphs in some way or another. At least I strongly believe that, and many others. So that's that, and there's a rich community around that that I think we should pay more attention to in that context, and we will pay more attention. I'm pretty sure about that. Another big success story is really search and optimization. Right, we know we could do chess since quite some years now, and that's an area that right, where we search, the search space size is 10 to the 20, 10 to the 50 range, which is huge. But a lot of people thought, well, Go, we won't be able to capture that because this is so much larger, much larger than the number of atoms in the universe. But by, and this is really interesting, by a combination of techniques that looked at supervised machine learning plus reinforcement learning, a more traditional technique, and Monte Carlo tree search, the combination of this really helped us solve this in an amazing way. And we're making even more progress in this area going forward, and generalizing these techniques in other interesting search. There's a lot of search and optimization all over the place, and we need to pay more attention to that, I believe. So, but not everything is rosy. And I think you know most of that, right? We're great at pointing our camera at the real world out there, and we can recognize objects. We can learn a lot about this. So we have highly capable AI, so that we can essentially drive autonomously in the world out there. But we have some very fundamental problems at the same time, right? So just putting a couple of colored patches on a stop sign makes today's AI system recognize something completely different, right? That can't be, right? I mean, if that at the lowest level, this is what we build our systems on, then we're in trouble. And I'll come back to that. And the same thing, right? If we just adding a little bit of structured noise that we as humans don't even perceive, makes a panda look like, or being recognized as something completely different, obviously we have problems at this case, in this stage. And I'll come back to this in a second. But before I go there, I want to give you a little bit of insight of how we approach this problem, right? And actually that's part of a little bit of my history, because when I joined DFKI, I was a graphics person, right? I'd never taken an AI lecture before, and I was wondering a little bit, what can we do there? What can we do together? And how can graphics and AI actually do something? And so I want to tell you a little bit about how I see this, and we see this this collaboration. And so my group in the DFKI is called Agents in Simulated Reality. And one of the key elements, and you kind of saw this coming maybe, is that we're aiming at what we call trusted AI. So AI that can really be trusted by humans. And our contribution to that is threefold. On the one hand side, we work on explainable AI, specifically on designing AI systems that can provide guarantees, right? That don't suffer from some of the artifacts I just showed you. And through providing that guarantees are also understandable and can be trusted by humans. And so it's really fundamental AI research. On the other hand, we work on something we call digital reality, and I'll talk much more about this, where the idea is to generate synthetic data from parametric models and simulations of those models. And using this synthetic data for training, for validating, for benchmarking of AI systems, and eventually, and we have various projects that go in this direction, eventually being able to certify AI systems based on an analysis, based on the performance of the AI systems. And I'll talk more about this in a second. And all of this, underlying all of this is also research on AI platforms and high performance computing, because both the simulation as well as a lot of the AI computation requires a lot of compute power. We have to do this reliable and efficiently. And so I'll talk briefly about some of the work in this area. So what are we doing here? I mean, a little bit older research is really a multi-agent system. So one of those autonomous systems that I talked about has been, for instance, used to controls for over 13 years, I guess now, 24/7 Steelworks, not far from here. On the graphic side, which might be closer to some of your research, we do a lot of, we have done and we are still doing a lot of real-time ray tracing research. Actually, I think still 2/3 of the Embry team at Intel comes from my lab. I was actually involved when NVIDIA kicked off some of their ray tracing work, and AMD is doing work in this area. We continue doing this. We actually published work on custom ray tracing processors, our RPU work at SIGGRAPH 2005. You might have seen this, and nicely enough, NVIDIA has published their hardware, which of course builds, certainly adds a lot on top of what we've done back then. But I think this has been, at least to some degree, influenced what is being done now. And as you see that Intel and AMD are introducing ray tracing hardware into their graphics cards, it's amazing to see how the research that has happened 20 years ago has really made it inroads into fundamentally changing the compute infrastructure on the graphics side. And there is a clear commitment by NVIDIA and I would assume by all the other companies as well, to really make it possible to have fully ray traced games going forward. And you probably have heard that from NVIDIA. We do a lot of work also on efficient lighting simulation. Our VCM, vertex connection merging algorithm, is really part of most commercial renderers, including RandomMan and V-Ray and Corona and other renderers. And this will become relevant in a second. So I'll come back to this. There's our work on doing optimal multiple importance sampling, really at the core of rendering today, together with Jaroslav Krivanek and his group in Prague, SIGGRAPH last year, or variance-aware path guiding at SIGGRAPH this year. Don't want to go into detail, but I mentioned this here, which seems to be completely unrelated to AI, but I'll promise I will come back to that. And some of the work we're doing here is highly relevant for what we're doing in AI. Instead of working with hardware, we kind of stopped doing that. We work a lot on compiler as well. And again, you might think, what on earth did that have to do with AI? But it's absolutely crucial for a lot of the work we're doing to implement things very efficiently, because with the compiler, NEDSL compiler framework, again, which was shown at SIGGRAPH last year with the rodent paper, I believe for the first time have developed a technology where we can formulate high-level algorithms at really textbook level and be able to map that to hardware very efficiently. And we're actually beating across CPUs, GPUs, and we're currently, we have prototype work on FPGAs and currently working on a publication to use exactly the same high-level code and the high-level algorithms and map them to different hardware architectures, and then even beat the hand-optimized codes, or at least get very close to that. But in many cases, even beat the hand-optimized implementations on each of the hardware architectures. And that makes a lot of things possible that required a lot of manual work when we started, for instance, implementing ray tracing on SIMD architectures back in the days. Yeah, this is the SIGGRAPH paper rodent from last year's SIGGRAPH. So we do a lot of work also on autonomous driving, and I will use this in the context to motivate some of the work we're doing, and also showing you how that link is between the AI world and the graphics AR, VR world that we all live in as well here. So this idea of digital reality, of using AI to optimize and certify AI by building models, simulating those models, generating synthetic data, and coming back. So, and the main driving force, and I mentioned this already, is how can we avoid a situation like this? You might have seen this image. This is the person that has crossed a 4-lane street. The car has seen that person crossing all of those lanes for almost 6 seconds, if I remember correctly, and has recognized that there is something, but has decided, that was the Uber accident, the system from Uber has decided there is nothing to worry about, and did nothing, right? And that person was killed, of course. Was hit by the car and was killed. And we all agree this can't happen, that this should not happen, right? But really, the scary thing from my perspective is there was a team of, I don't know how many hundred people building the system, and they were not aware of the limitations of their system, that it would not be able to recognize that person. By the way, it wasn't as dark as it seems on this photo. So it wasn't actually as bad. Anyway, so I think we need to do something here. And the point is, right, we can drive, and Uber at the time was actually able to reasonably drive. So we had the functionality of autonomously driving a car, but we need to be able to certify, to validate, and to provide guarantees about what the system can do and where it stops working. And we don't have that ability now. And we need to do so according to well-defined standards. That's a completely different story I don't want to go into here, but at some point we need to define what those standards are, and certification, of course, is always with respect to some standards. And why is this hard, right? It's hard because our world is so extremely complex in terms of geometry, appearance, the motion of objects, weather, right? A wet street looks completely different than a dry street, complex environments of plants and complex arrangements of people and cars and bicycles and whatnot. And despite this complexity, our AI system must reliably make the correct decisions and accurately, right? If there's a kid jumping out between cars in front of the car, the driving car, where the autonomously driving car, right? We rely and we demand that the AI system will detect this as quickly as possible and respond in the best possible way, even if we as humans might not be able to do it, but we demand different things from an AI, and I think we're correct in demanding this from a machine, essentially. And the problem with this approach is that we rely a lot on deep learning and other learning techniques. All of these learning techniques require large amounts of data, but specifically for kids running in front of cars, we don't have data and we don't want data, right? I mean, this idea that's still promoted by some people in the autonomous driving industry of this question of how many millions of miles do we have to drive until our cars are safe is crazy, right? Because it essentially would mean how many miles do we have to drive until we've hit enough kids, so we recorded enough data that we can now learn from that data how to avoid this in the future. And I think we all agree that this is probably now not how we want to do AI research, right? And this is exactly where this idea of learning from synthetic simulated data comes in, right? I would even argue it is required to solving situations like this. And actually, it's funny, we're actually doing a lot of this in other contexts, right? If you develop a car today, safety is essentially provided through virtual crash tests. These crash tests are mostly done with finite element programs in the computer, right? And only at the very end do they actually crash some real cars, not so much to validate the safety of the people in the car, but essentially only to validate that the finite element did the right computations. And we essentially want to do something very similar for AI. You can also think of this, we do the same thing in other contexts, right? An airplane pilot, we're not allowing airplane pilots to fly airplanes unless they have, in many dozens of hours in a flight simulator, have shown that they can handle all of the emergencies, like, I don't know, engine failure and what you name it, right? So we should do the same thing for AI systems. They need to prove, they need to show us, they need to provide evidence that they can handle the difficult situations, and they need to show where their abilities end as well. So here's the whole idea, the whole story in a couple of slides. So starting by training, the car industry started by training cars with real data, right? This is, they even built large test tracks, which of course you can't scale this up to all the possible scenarios. So it's costly, it's difficult, and non-scalable. And so the car industry has actually started already quite some years ago to train their cars and to gather data through simulations. And funny enough, those simulated digital realities happens largely with game engines, right? And the models come from artists. And you could question, like, how good are those models? How good do those models represent reality out there? And I always use this example of when a pedestrian approaches a street from the side, one of the key questions as a human driver is, does that person stop or will he cross the street, right? Because you either have to brake or not. And we don't even think about that. We immediately understand that this person will or will not stop. And the only way we can tell is by looking at that person and noticing this subtle change in the motion of that person that tells us, oh, he's slowing down, he's probably going to stop, right? So we can do it as humans, but if we don't have that subtle information, and no one of us can probably explain exactly what he is seeing there. So we can't teach that to an AI if that information isn't even in the model, right? So that is probably a very limited approach, what's being done there right now. And so what we're suggesting to do instead, to derive at this digital reality that we then want to use to train the car, is that we actually start by reality out there from all of the observations that we have about the world out there. And we build partial models about geometry, materials, behavior, motion, and so on. So for example, we're working in various topics here, various aspects of this. So for instance, we're building models about pedestrian motion, so motion models. And we also build models about the behavior, right? So layered on top of the motion, so the decision by pedestrians to whether they cross the street given the velocity and distance between cars and things like that. So that's the first step, and we use AI for learning those partial models. And I'll talk a little bit about more of how we do that. The second step is that we then put together those partial models to model relevant scenarios, in particular critical scenarios if we stay with the autonomous driving setting. So for instance, a kid running in front of a car, right? So we need models of kids, of their motion, of their behavior. We need different environments, different other cars, and so on. And we use AI to reason about these scenarios and to find which cases are relevant, right, or dangerous, right? If we can, for instance, reason about the fact that the kid is a kilometer away from the car, then, well, maybe there can't be critical. This is not a critical scenario, while right, others are. And so we use this information to also identify situations that are relevant for learning of AI. And this will actually come back in a second. And then then we use the parameter space of these models to create concrete instances of these scenarios. So large kids, small kids, from left, from right, fast, slow, at day, at night, with snow, rain, fog, or whatever, right? All of those variations. And since we have models, we can actually generate them. And there's various ways how to do this. One of the ways we're looking into this is importance sampling, using Monte Carlo and importance sampling in these high-dimensional spaces, which actually is closely related to some of the, for instance, path guiding work in rendering, which is a very interesting, but maybe non-intuitive link here. And I'll come back to that. The third step is that then we simulate these environments, and not just the traffic scenario, like we animate the pedestrian, the kid, and the other traffic participants, and so on, but we also simulate the sensors, the virtual sensors of our car, because what we, or in other words, such that we generate the data that a real car with its real sensors would perceive if it were in that situation, in this virtual situation that we've just modeled. And then here, then the critical part really happens down here. Now we're in this digital reality. Hopefully these are very accurate and good models about reality that we can then use to use this synthesized data to perform training of AI systems, specifically, for instance, for these critical scenarios for which we otherwise wouldn't have data. We can use it for benchmarking, right? Did our AI system somehow get better since last week? Or can maybe there was a regression for certain kinds of accidents? We can use it for validation, right? Like this training or this testing of an airplane pilot, just presenting an AI system with all of the difficult situation and saying, oh, maybe this sort of car can do it better than another one, and this failed completely. All of this thing, but also to certify, right? To have essentially a test, a catalog of test cases, and that might actually be a continuous catalog of test cases from which we then select and can formulate criteria under which the AI system can be certified. And then the last part, but really crucial part of this digital reality approach is that we at some point have to validate what we've learned through this loop actually applies to reality, right? Maybe our partial models weren't perfect, and we might have learned stuff that confuses our system when it's presented with real data. Maybe there's things we haven't modeled. Even more importantly, maybe reality has changed over time. And so our models from last year might not be accurate enough anymore, right? I mean, e-scooters weren't around 2 years ago, and our models would have been incomplete. And there's probably similar stuff happening going forward. So really, and we have to do this anyway. So we will never build one AI system. They have to adapt to the environment, and they have to constantly update their knowledge representation about the world. And so we have to go through that loop many times. Now, I explained all of this in the context of autonomous driving, but none of that is specific to autonomous driving. All of this works as long as we can model the environment that the AI system interacts with. And that's really important. Now, there are cases where this is impossible, where we don't know how to model that environment. And so we cannot apply it there. But I would argue for the great majority of cases, this actually is possible. And interesting enough, that is at the core of what we do in graphics, VR, and AR, right? So we have a lot to bring to the table, I would argue. And so what are we doing here? Hopefully you can see the animation. And if it were more interactive, I would ask you, what are you seeing here on the right-hand side? And the usual answer is a walking human, right? And I can only point out you're completely wrong. And all you see is white dots moving on a black background. But as humans, we cannot even avoid, right, interpreting the data with our background of knowledge about the world. And we're immediately interpreting the data in that context of what we know about the world. And AI can't really do this. AI today doesn't really have good models about the environment, right? Or very narrow, very specialized models. And so the question is, can we teach AI using models of the real world to be able to do that? Now, this is not exactly what we're working on. That's more the far-fetched demonstration of where we want to be. But I'm actually pretty sure we should be able to do things like that. So what are we actually doing? So I'll just want to give you in the last few minutes, give you a little bit of idea what the type of research that we're doing. So here we actually do motion capture of real pedestrians. This is actually in front of our university building here. We have a zebra crossing. And there's two types of students. They either walk up on the walkway to the bus stop, and they look backwards because the bus might already be coming. They have to run, right? And the other type of students actually wants to cross the street here, and they look backwards to see whether there's traffic coming from behind. And for the traffic, it's obviously important to know who wants to cross and who doesn't. And the question is, could we perceive that? And we're working on this problem. So you couldn't, for instance, perceive this through the turning of the head of the pedestrian, because right the people that look to that are continuing, they essentially have the same head movement, have the orientation of the head is pretty much the same as those crossing the street. But if you look at the hips and the shoulders, this is real recorded data. It's very clear that those who want to cross are efficient by already starting to turn their body because they want to cross anyway. Maybe they have to stop, but at least they're starting to turn. And now the question we are asking ourselves, is that something, can we model this? Can we then synthetically generate data? And from that data, actually learn to detect who of those pedestrians will cross the street and who won't. We do a lot of work on motion capturing, motion. We're not so much in the capturing part, but then motion, using captured models and processing of captured data to derive motion models. Don't have time to go into this. This would be an entire separate talk. But it's really interesting to see how modern, for instance, these dilated convolutional networks can really deal extremely well with some of this data here, even huge amounts. So we can add 90% of noise to our training, to our training label. So we intentionally give wrong information to the learning process, and it can still do the right prediction, even with 90% of the labels being completely wrong. Interesting, and we can talk long about how this works. Other research we're doing, for example, is how do we deal with these huge parameter spaces of the models, right? I mean, each of these pedestrians has many degrees of freedom in each of the joints, and the same amount of change in one joint is maybe rotating the pinky finger of that pedestrian by 10 degrees, while another parameter might be moving that person by 10 meters, right? We have, if we want to sample in a meaningful way this complex environment and try to identify what we haven't learned yet, and what information, what sample of that environment would provide us with new information, and which samples we already have accounted for and they might not be interesting for us. We have to understand that enormously large parameter space. And interesting enough, that's not a problem just that we face. It's a problem that many other sciences face, that have complex parameter spaces and want to kind of do something with it. So many people are dealing with this, including AI itself. There is a whole area of AI called AutoML and AutoAI, which does exactly that. It tries to optimize some of the parameters of neural network, deep neural network learning, and they essentially do similar stuff, and we're just in the process of setting up very interesting projects with very interdisciplinary teams that kind of look at these problems from various different ways. And it's largely an unsolved problem with lots of really exciting challenges, at least from my point. Another part that I quickly want to talk about is verification versus validation. Right, I mentioned that at the top, we might be able to verify that if the kid is too far away from the car, nothing can happen, and we don't need to do testing. Right, so verification is more a top-down approach because it can usually not deal with too complex environment, limited expressiveness and complexity. While validation is really expensive, and we can never complete we cannot prove completeness, right? But the combination of two is really powerful, I believe, and so we're exploring in our research this connection here. Find a path, like a top-down and a bottom-up path, trying to combine the two. And so it's really all about verification and validation, combining the two techniques. I think there's a lot of powerful research to be done here. And these are two communities that don't necessarily talk to each other, at least not that much. Another part, and that's much closer to a lot of the work closer to a lot of the work we do in graphics, is radar rendering and radar simulation, for example, right? And both radar and light is just an electromagnetic wave. So you could think, well, maybe I can just use the same technology. Well, yes, in principle, yes. But a lot of the stuff doesn't work because we have to take wave effects into account for radar. It's polarized, we have interference, multipath interactions, and many other things, diffraction. Still, we're also somewhat different goals, right? It actually turns out in optical rendering, we mostly focus on diffuse parts, well, with some highlights on top of it. But in radar, we essentially only are interested in specular light transport. All the others just distribute energy too much, and with a high noise level, we wouldn't see those signals at all. And so it actually turns out that a lot of the research in rendering in the last few years, in particular the work on path guiding, and I mentioned one of our papers there, is highly relevant in this area because it's essentially trying to figure out what are these caustic, these specularly reflected, we call it caustics. How do we best render them? How do we best find those transport paths for light? And we have to do the same for radar. And so it's interesting that the radar community, for example, hasn't actually looked into this much. And they're using typically a lot of finite element methods. They use a little bit of ray tracing, but it turns out they don't use a lot of the techniques that we've developed. And here's just some examples of our recent work. So simple examples where we have an analytic solution, we can perfectly match this more or less. Here is a little bit more complex. This is rotating a narrow box with a narrow side, and you would expect a strong peak here. Here it is in the middle, but because of interference patterns, you actually have a dip exactly where you would expect the maximum. And so our simulation and the measurement match almost perfectly here. And even more importantly, this is a more complex environment, or more complex scenario, not that complex, but with the path tracing techniques that have been used in the radar community, you see that, right, what the results are is far from what you would expect to see, except at least for once you are a little bit away from the sensor. So huge noise, and you don't see any of the features. And by adding things like texture filtering, of course, which we in graphics know really well, by path guiding, we get much better results already. Then adding a little bit of discrepancy sampling essentially brings us most of the way to actually get much better results already. And we're in the process of really applying this in a larger context. And so really so essentially the difference between this and this, this and this result, right? The starting and then using a lot of, this is using graphics technology in a different context, and we get dramatically better results. So, and then one of the questions that I'll come to an end in a second is maybe we actually need to build different renderers today, right? Because the gaming renderers and the film renderers, so to say, they focus on, in some sense, on the wrong goal. They focus on nice images and fast and nice images, right? But what we really need for this kind of work is focusing on correct images. So essentially, maybe in the limit to have an error bar per pixel and being able to validate that these these results are actually correct. So I've been discussing with various people the idea of a predictive rendering engine. We actually have a large European project that looks into this with many other top graphics labs here in Europe. So wrapping up, I think there's huge opportunities to link AI with AR, VR, and it's probably through that digital reality concept that I mentioned earlier. So in the one sense, AI has to offer a lot of technology, for instance, and this list is certainly incomplete, better technology for learning models, right? And that's already happening. And I see some papers here at this conference going in this direction, right? And many other graphics conferences. Learning shape models, appearance models, motion models, and also maybe more general models. Improved and integrated interaction technique, right? I mean, we have intelligent avatars or AI-driven characters, gestures, speech, dialogue. There's a lot of tools that come from AI, if it's just speech interaction, right? Or gesture generation, natural gesture generation, dialogue engines. This idea of optimizing across large parameter spaces, like I mentioned, auto AI, auto ML, or Monte Carlo approaches that have been developed on the AI side, I think was highly relevant also here on the graphics side. And also this integration between symbolic and sub-symbolic approaches, so between reasoning and learning. I think there's a lot of happening right now that we here in graphics and visual computing can benefit dramatically from. And again, I think some of the papers in this conference go in this direction. Even in the first session, I found a couple of papers that are relevant here. But also in the opposite direction, right? What do we, as, if I may say, graphics people have to offer to AI? I mean, we have a huge experience of building interactive models of the world out there. We know how to build large-scale simulation platforms. We have a tremendous set of tools for visualizing stuff, for interacting, interacting with those systems, for exploration of data. So just the ability to visualize AI data in context, the whole idea of explainable AI probably involves some sort of visualization, right? I think there's a lot we have to offer here. And yeah, specifically for explainable and trustworthy AI specifically in Europe are a key topic right now. There's a lot we can do to bring things together here. And so as takeaways, additional takeaways, I guess, I would argue digital reality, as I presented, is really a fundamental tool in AI. It's underlying, and specifically, if you approach this from a graphics context, I think it makes a lot of sense. This continuous learning loop is required. We have to adapt to a changing environment. We have to be able to certify and validate AI systems, because without that, who would trust in AI systems given some of the fundamental problems we're seeing? And that in turn requires a lot of HPC and simulation that is very close to the heart of AR, VR, and graphics people. But having said all this, I mean, we're just starting on this challenge, right? There's a lot we don't know. There's a lot that we that we still have to figure out. We don't know how accurate our simulations have to be, how accurate our models have to be. Fundamental questions that we can't answer yet. And I think we need to bring people together. And so this CLAIR that I mentioned in the beginning, this organization, I believe is really fundamental on the European side, at least, to build, to integrate people. And I think graphics and visual computing people should really engage with AI, and CLAIR might be one mechanism for doing so. And one of the things that CLAIR is arguing for is building a CERN for AI, a large central space here in Europe where we can bring a lot of that research together. And so I think there's plenty of things that we need to do to go forward. And yeah, so with this, I'm done with my talk. I hope I could motivate you a little bit. I saw there's a lot of papers going in this direction or in some AI direction already. I'm glad that I got the opportunity. So again, thank you very much. And I'm looking forward to any questions you might have. And so we can have some discussion.
Okay, great.
Thank you.
Yeah. Thanks very much, Philipp, for the very interesting and inspiring talk. I think it was your talk was clearly showing the connections between virtual reality, graphics part, simulated worlds, and the AI part, which is very relevant to this conference. So I want to turn to the audience, so you can type your questions in the Q&A. Or you can also raise your hand and ask the questions yourself. So I just checked the Q&A already. And in the meantime, I have a question. So this digital reality idea was very interesting. Using the real world to simulate the digital world, and then using the digital world to make the test, like the car simulation, for example. But I'm just wondering to what extent we can really get close to simulating the reality in the digital world, because it seems to be like a little bit of a chicken and egg problem. And referring to the flight simulator situation, for example, I can imagine probably the flight simulator case is a little bit more, it's a complex environment, but might be a little bit more, controllable environment with respect to car simulations or self-driving cars. Because when in self-driving cars, you have a lot of pedestrians, people involved. And when people are involved, of course, there's a lot of uncertainty going on. So to what extent do you think it is possible to really simulate a lot of different situations? Of course, we don't have really so much of a choice because we cannot create every critical situation. So that is the path to go. But to what extent we can cover
you're hitting the nail on the head, or however you want to say that. And yes, it is a chicken and egg problem, but that is how you solve chicken and egg problems, by iteratively refining the approach, right? And so I think this idea of well, first of all, we already have very good models of the world, and I mean that a lot of people in graphics are doing exactly that. We're building models of the world, and so we can build on top of that. So we have pretty good models on the optical side. As I mentioned, radar is quite a bit different. And there's a lot of wealth of data that graphics, AR, VR people can bring to the table here, also about simulation. But then if we combine this with the AI technology, right, we don't have to build those models by hand, which is admittedly what we've done for years, right? So we can hugely benefit from the AI technology to really learn these models, hopefully more or less automatically. Currently, in many cases, we still need to lend a hand there. But then the last part, and I didn't have too much time to talk about this, the fourth step of this digital reality model is really crucial, because once you have a model, and I would argue we already have AI models that understand a lot of the real environment out there. One of the elements we're working on is, for instance, is Bayesian deep learning, where you're not actually learning a single result, but you're learning essentially probability distributions. And these probability distribution tell you something about the confidence that the deep learning network has in interpreting the image. And so, for instance, you can use this and other techniques to identify like what element in the scene does the AI system have difficulty identifying, right? So my example that I often use is, well, maybe there's a kid doing somersaults on the street, right? Maybe we didn't model that, right? So what we would expect that the AI, that this AI system would tell us, there's something on the street here. I don't really know what it is, right? But sometimes it looks like a kid. It would record this data and maybe automatically at some point, but maybe manually for now, we would take this data and steer our models, adapt our models, or maybe add new models to help us deal with situations that we're not aware of. So it's really this chicken and egg incremental way of improving our understanding. And actually, I would argue, actually, we have a really interesting project with Nida Rümelin, a German philosopher, where we argue, or at least I argue, they see things slightly differently. We argue that humans are doing exactly the same thing, right? We have a model about the reality. We're constantly behaving as if that model were true, and if it's not true, right, then we actually adapt our model and learn that maybe we should avoid that danger over there in the future. I think there is a lot of similarity here. Sorry, that was a fairly long answer to a simple question.
Okay, no, thank you. It was really good to emphasize this last part, closing the loop, especially.
Yes. Yeah,
okay,
I think it's critical. That's really the critical part.
So I look at the question and answer. So one question from Pavel: what is your take on using machine learning for rendering to learn real data instead of simulating it? For example, differential rendering techniques.
Yes, so it's definitely interesting. But if you look at the complexity that we're dealing with in realistic rendering today, right? We have to solve high dimensional integrals. And so while those and I might get in trouble here saying this. So there's great work being done there, don't get me wrong, right? However, I doubt, and a lot of colleagues agree with this, that this will really solve the rendering problem, right? It will be able to synthesize meaningful, well, meaningful, I'm not so sure, but convincing images that are convincing to a human. I'm not sure, or actually I'm quite skeptical that these techniques will be able to solve the rendering problem. And as I mentioned, and as I tried to argue before, I think we need to do this, and we need this accuracy, because if we don't, then we're actually looping within AI. We never go back to reality, because essentially simulating the rendering equation essentially binds us to the physics of the world out there, right? And this doesn't happen if we do everything with learning. Having said that, I'm really excited about the work that's happening there, and I keep discussing with some of my colleagues of how far you can actually push it or not. Very interesting question, but I'm skeptical.
Okay, thanks very much. So I think that is it for the questions. So also regarding the time, I think we should wrap up this session, and we still have other demonstrations to make before the next session. So I would like to thank you very much for your great talk and the inspiration on behalf of the audience.
Thank you very much for the opportunity, and I should also mention, if anyone is interested to talk offline or interact offline,
yes, for sure. For the Slack communication will really help for that as well. So I'm sure there will be more lively question and answering on that. Okay, great. So so I would like to now continue with the poster and demo session. So for the posters and demos, we have 1 minute teaser. And yeah, so I hope, yes, the host can start playing them already. Okay, they are on.
Thermal comfort and safety is a key issue in VR and AR applications, as users often hold or wear smartphones, head-mounted displays, or smart glasses for an extended period of time. In this paper, we design a framework for smartphone thermal temperature measurement and analysis. One measurement framework consists of Android smartphones, infrared cameras for thermal temperature measurement, and one robot for emulating 3 types of user behaves while using VR and AR applications: rotating, walking in a cycle, and shaking head. We measure and analyze a comprehensive set of data, including the battery power consumption, smartphone surface temperature, and the temperature of key hardware components. Our results show that in-depth research on hardware and software support for more effective thermal management is needed to enhance user experience in VR and AR applications.
This work focuses on captioning for immersive environments with the aim of identifying how to display them for an optimal viewing experience. In previous work, it was identified that in order to get useful feedback from users, you need to be able to present them with a fully working prototype. In this research, we have developed an environment for rapidly producing immersive caption scenarios, which combine fixed and headlocked captions with new guiding modes and custom rendering styles. In addition, further data is used to enhance the range of experiences, such as per frame position of captions, allowing captions to follow the characters, and the use of responsive captioning to resize captions on the fly.
Hi, I'm Dan Hawes. I'd like to invite you to our poster session to find out how virtual reality gaming can reduce anxiety and increase cognitive bandwidth. We'll discuss the issue of student anxiety and how we might apply theoretical and technological thinking to help solve the problem. We'll present our proposed theoretical framework, something we call the cyclical priming methodology, or CPM. It starts with a scarcity mindset. We apply technology, cognition, and learning insights to create an abundance mindset. We apply a technology solution, something that we call VR experience priming. If you want to find out more, come join us at the Tuesday poster session. We'll see you there.
Two-way, two-lane highway work zones typically place human flaggers to safely navigate traffic in each direction. When training inspectors of these temporary traffic control setups, current practices include the review of standards and protocols in reports, pictures, and videos from previous inspections. In this project, we developed a virtual reality training module that situates trainees within a moving inspection vehicle entering an active work zone with flaggers. The main objective of the proposed training module is to deliver a realistic, immersive experience to trainees that matches the real world while also introducing them to current traffic control protocols and standards for flagger operations. When shown this training module to state DOT staff and training personnel, they responded optimistically about its potential. Since traffic control inspection requires high levels of spatial attention, current training practices can benefit from immersive training modules such as this one.
Okay, so thank you for the posters and demos teasers. So after this session, we are going to continue with the poster session. You can follow the program to access the links to go for the posters and demos to get more information. That will be in Mozilla Hubs, I think. In parallel, there will be a workshop on AI XR, so that's also possible. So after this session, you have two options to continue. I would like to thank again to our keynote speaker today and then to the audience for their participation and the questions. Yeah, so enjoy the rest of the conference. I'm not sure if Wolfgang will take over.
Normally not. I don't have an option to raise my hand, so I'm just popping in. Yeah, thank you very much, everyone who contributed to the session. Keynote speaker sharing, very great keynote. Really liked it also, the one slide where you'd say AI to VR and VR to AI. So really the relation between both. So perfect. The reason I'm popping in is quick comment. If for the Mozilla Hubs, the links to the rooms are on the website now. The one where you have also the links to the Zoom rooms with the program. You find the link to the poster where you have the poster. In front of each poster is a link. If you go to the bottom of the page, there is an overview with all the rooms where you can go also directly to the rooms. Just one comment, AIVR told me that there was a little bug in the URL, but they fixed it. So please reload the page before you go there. Good, that's it from my side. So thanks to everyone, and that closes the session now. Good, Xiao Hang, you can stop now the live stream on YouTube and also stop the recording.